Hi and welcome. I'm trying to learn particle physics today, the weak nuclear force, and after we've done that, we're gonna do wrist training. And if you participate in wrist training, then it's better the arm wrist. Before we're going to the weak nuclear force, we're gonna read the end of chapter neutrons, which is part of the chapter here, because we went a bit fast on it. Results from mini Bonnet type of experiment, released in 2018, muddied the water still further. So question if there's a fourth neutron somewhere. They showed a large anomaly than before, a larger one. Some hailed this as strong evidence for the existence of this hypothetical fourth particle. But if, as the real fourth neutrino exists, then more neutrinos shouldn't just transform into electron neutrinos on the way to a detector. Some should disappear as well. Yet more neutrinos' disappearance has never been seen. During the 15 years that Mini Bonnet was ticking away, physicists set up a number of smaller experiments to probe for this disappearance explicitly. One of the biggest is called MINUS Plus, based at Fermilab, Illinois. Over the 10 years it and its predecessors had been running, more neutrinos have steadfastly refused to vanish. So never, these muons sometimes switch to become electron neutrinos, maybe even tau neutrinos, but if this muon neutrino would switch to this hypothetical fourth type of neutrino, then it would be basically vanish because we can't find the fourth neutrino. But it never vanishes. It was never seen to vanish today. While theorists, this places severe limits on what any potential stereo neutrino may look like, if it even exists. While theorists develop ever more exotic ideas about what could be out there, experimentalists will keep on searching. Okay, theorists are thinking about what is not with the fourth one, and experimentalists are searching for. Using detectors around the world, such as the Ice Cube Neutrino Observatory, an experiment to measure cosmic neutrinos passing through Earth in Antarctica. Okay, so in Antarctica there are people having this Ice Cube Neutrino Observatory, and we're looking at their neutrinos. And they hope to place ever tighter bounds on the disappearance of muon and electron neutrinos, as well as the rate at which one turns into the other. Okay, we're trying to find out how often such a muon switches with the electron neutrino or to an electron neutrino, and what's the other was to find out the rules for that. More experiments are planned soon. One is the Deep Underground Neutrino Experiment, or DUNE, Deep Underground Neutrino Experiment, DUNE, which will fire an intense neutrino beam 1,300 kilometers in straight line through Earth for Fermilab to the Sanford Underground Research Facility in South Dakota. Has the Earth such a great bow, but from Illinois to South Dakota in just through Earth? Okay, it's not true. It's just in straight line through. You know, how does it work? I want to see the graph of it from South Dakota to Illinois. I don't know exactly where states are. Okay, we are firing an intense neutrino beam 1,300 kilometers in a straight line through the Earth from the Fermilab in whatever now to the Sanford Underground Research Facility in South Dakota, where a 70 kiloton volume of liquid argon will register their presence. Yes, this is the thing with the neutrino detectors. We're having some types of liquid in there, so it's argon in this container. These are 70 kilotons, so this sounds like odd. And with that way, we want to catch these neutrinos which the other people 1,300 kilometers away have sent through the Earth. Such huge undertakings are worth the money and effort, says Carlo Rubia, a former head of particle physics laboratory at CERN. This is one of the areas in which new discoveries are possible, but we don't know from which directions these discoveries will come. So we have to take a very courageous view to find out what's coming next. Okay. Fundamental force. One of the fundamental forces is the weak nuclear force. Governing theory. Electroweak theory. Unified theory with quantum electrodynamics, the theory of electromagnetism at high energies. Okay, that is the main theory, that is part of whatever, that is some type of, that is part of that theory or whatever. Mediator. W and Z boson, predicted in 1968, discovered in 1983. I think mediative, it means this is the thing which is doing the work, basically the transport. This is the thing which is doing the thing. I don't really know what the word mediator means. But I think it means that is the thing which is doing basically the job, on which it is acted out or through which is it acted. Through the W and Z boson, which were predicted in 68 and discovered in 83. The typical range are 10 to 18 meters. So not that much. Electroweak force 10 to 18 meters. Why does such an electroweak force stop? Why do some things go on forever and others? And why 10 meters? Why not 100? Why not 1? Of the 4 known fundamental forces, okay, there are 4 fundamental forces. The weak nuclear force has the least obvious purpose. Yes, what's the purpose? That's the big question. Okay, we don't know it really. Its effects were first discovered at the turn of the 20th century, in the place where it is most obvious at work. Okay, there are 4 types of fundamental forces in the universe. Whatever the other 3 ones are, one of them is the electroweak force. And this weak nuclear force has a range of 10 to 18 meters and acts through the W and Z boson. And there are no very good explanations what's the use of it. But it was found around 1900, so around 1900 it was first discovered when people were working with it. In radioactive beta decay, I still didn't really know what it is. In the most common form of this decay, beta minus decay, a neutron decays into a proton, also splitting out a negative charged electron, to conserve electric charge. Beta plus decay does the reverse and turns proton into neutrons. This amounts to an ability unique to the weak force to change the flavor of the quarks that make up protons and neutrons. For example, switching a down quark to an up quark or vice versa in beta decay. Right, let's. I don't think we should read on. Let's go back. Maybe we're going to explain it a bit better. But okay, in radioactive beta decay. Okay, people are doing radioactive beta decay. Now, what is it? And in the most common form of this decay, that is beta minus decay. And there is a neutron, and it decays into a proton, and it spits also out a negatively charged electron to conserve electric charge. So there's a neutron. A neutron has neutral electric charge. How can a neutron decay into a proton? Whatever. Because it does it and becomes basically positive, it has to say also, I'm becoming negative, I'm staying neutral, so it's spitting out an electron. We know what it's about. Beta plus decay, so that is not beta plus, that was beta minus, so an electron. Beta plus decay does the reverse and turns protons into neutrons. So there's a proton, and that's turning to an electron and spitting out a neutron. Whatever, it's some type of whatever. This amounts to an ability unique to the weak force to change the flavor of the quarks that make up protons and neutrons. Protons and neutrons can have a flavor, for example, switching a down quark to an up quark. Okay, whatever. This weak nuclear force is important to switch these states of down and up quark and these different types of things, which the standard model says are there around. I don't have time it. If you were here for particle physics, you can go directly to the next part of particle physics. We will read on about the weak nuclear force. We will do, did I say again, actually just weak nuclear force, I think was it. If you were here for particle physics, go directly to the next part of particle physics. We're going to do now the wrist training. If you stay and participate in wrist training, then it's without risk. Go ahead and stand, arms up, hands with the fists, and bring them down. And up, and there is the spotlight. And the next exercise now, the fists to the inside, hands to the outside, and there's the flashlight. We're having 3 rules. The first rule is that we are stopping immediately as soon as there's pain. Next exercise, flat hands and bend to the inside. The second rule is that we're going only as fast as we can go with a little bit of it. And the third rule is that we are not overdoing it. We just want to strengthen, not to exhaust. The pancake flip, flat hands and up. And directly to the next exercise, the dinosaur now with the T-Rex in the morning. Hands out, flat hands, and we bring it down and up. Now, if you want to take a break, do it at any moment. We have quite a lot of exercise. And we're also ready for the last one. And now we're going to do a triangular, no, not a triangular, a quadrangular castle architect. Both hands out and the fists into the inside. And up. To the outside. And down. To the inside. And the other way around. Next exercise, we clap anxious to have fever. Arms next to us, hands onto fists, and bring the fist down into flexion. Press a bit against it. Pull a bit from the outside. Press a bit from the top. And from the ground. And on to the next exercise. Hand next to us, hand on the fist, bit down into flexion, press against it. And from the outside. On to the next exercise. Cautious breathing. Fingertips of one hand on top of finger nails of the other hand, and we open. Last time. And this will be. And now the T-Rex in the gym. If you are doing it before the tennis ball, then just make a strong fist. If you're doing it with the tennis ball, press with moderate force onto the tennis ball. Release, and a second. Release, and okay. Let's switch. Press again. Release, press. Release, and on to the next exercise. Vierte is nu Sylvia's sector. Twist and the opening and the top. And on to the next exercise. The bicycle bridge. Flat hands and bend the middle knuckles. And then open again. Last time. I know. Now a frog anxious to fever. If you want to take a break, do it now. This exercise is a bit intense. Down flat fingers and up strong fists. Down flat fingers, up strong fists. Down flat fingers, up strong fingers, and strong fists. Good. Also last time, and next exercise. Claws. Flat hands, and make claws. Up again, back claws. Up. Last time, and up. Next exercise, again more intense one. Arms in, strong fists into flexion, and out into extension to flat fingers. And in strong fists flexion, out extension flat fingers. In strong fists flexion, out extension. And last one. And to the next exercise, the biceps, flat hand, and bend the knuckles and press on all four fingers. Your hand, bend it, press on all four fingers. And out. And the last exercise, go to step stance, the unfolding rocket boosters, long arms, strong wrists, and bring these strong fists into flexion. And now out into extension flat fingers. Inside strong fists flexion. Out extension again. And change. And last one. And last exercise, just cover with moderate pressure over the middle part of the lower arm to relax the extensor digitorum muscle. And on the other side. And that was Wristtraining. I thank you very much, and until next time.